You are a mathematician, trained, and so on, if you want to tell us.
That's right, yes. So I trained as a mathematician. My field is probability theory, actually. I've worked as an academic for a number of years and in industry, in the financial industry especially, but also some engineering. And then about 15, 16 years ago, I transitioned to teaching. So I teach at the high school level. I teach gifted students. And I'm teaching at a school called the Nueva School here in San Mateo in the peninsula.
Nice, cool. Yeah, so, well, we invited you here for a couple of reasons. First of all is the math education.
Yes.
And Kilton is also very into this idea of making it more accessible and easier for everyone.
I
and
love
also
to hear that.
Yeah, and using also different tools. I mean, and I think
Yes.
that's the same philosophy that you have, if you want.
Right. So for a number of years now, I've been focusing my work on innovative approaches to presenting math, both the pedagogy, but also specifically the language we use to describe mathematics. And I mean, when I say language, I mean the symbols, for example, how we represent the ideas.
And do you think, because we were talking about it, and actually Kilton has good ideas about it, the fact that the educational system from middle school to college limits not just the understanding, the exploration of math, but maybe also the potentials of math.
Absolutely.
Because there are so many new discoveries that can be done, and they cannot happen because these institutions, I mean, maybe it's not the fault of the institutions, but the educational way, the pedagogical methodologies and so on, but even just the structures that are there since centuries, hold on all the potential of math. What do you think about
Well, I mean, for one thing, I should start by saying it's a difficult problem. I don't purport to have the answers, but let's start by acknowledging the scope and challenge of the problem. You're trying to teach millions of students. You have to come up with processes that are transplantable and in different settings, in different contexts, and can be composed well together. So you can build, let's say, what you learn in 5th grade with what you're going to learn in 6th grade. That these things stick together nicely. So most people, in the end, I'm making a de facto statement, right? That after having experienced the traditional mathematical education that almost everyone nowadays has, you would be hard-pressed to find one person who will think of mathematics as a creative endeavor, as an artistic endeavor, the way I do, the way that practicing mathematicians do. Most of them, they will think that it's a dry field that mostly was discovered a while ago, and there's some esoteric, cryptic things that you either get or not get.
The educational systems is limiting the potential of math. That's what I was trying to argue before. So do you think also cryptography, the way we understand it, the systems that are in place, they're very good. They exist, though, because we have that knowledge of math that makes us think that they are secure. But if we would have a different educational systems, or we would be able to explore more potentials, and with the quantum theory we do now, these systems are much less safe today.
Yes, I think that, strictly speaking, what you said is accurate, and that the advent of the quantum information revolution, this new way of seeing quantum mechanics, has opened our mind to other ways of seeing what we previously thought were computational bottlenecks. Cutting edge in that field, as far as I'm concerned, are applying quantum techniques in that space. In places where we thought there was a bottleneck, there's some technical issues that I'm referring to there, having to do...
So concerning cryptography, then we can infer that...
Similarly, with cryptography, the main sort of resource we have access to in classical cryptography is the computational hardness of some problems. For example, the factoring of large prime numbers is considered to be a canonical example of what is called an NP-hard problem, basically a problem that we don't anticipate classical algorithms to be able to solve in what we call polynomial time. In other words, that what the polynomial refers to is as you increase the size of the code, how does the time scale that is required to break that code? And if it grows super polynomially, in particular if it grows exponentially, which the fact that an exponential algorithm exists to solve it comes with the moniker NP. It means that, in other words, you could just kind of dumbly search the space of all possibilities. That is an exponentially large space, but if you were systematic, you could go through all of them. The problem is it would take the life of the universe to do.
And still that would be an assumption.
It would be an assumption.
Would still an assumption that takes that, but they are hard to find even as assumption.
They're very hard to find, absolutely.
But it's still
it was
an
a big
assumption.
discovery in the 70s when this was the current RSA system, for example, which was developed, the one that is used most broadly in classical cryptography. It was a big discovery that this could be described, sort of formally this way, and to be proved to be equivalent to basically the hardness of these NP-hard problems. The fact that problems of this kind are exponentially hard is a conjecture. Is one of the famous millennial conjecture or millennium problems. That, in particular, the fact that P is not equal to NP, the class of problems that are solvable in polynomial time, the conjecture states, is different, distinct from the much larger class of problems that are describable in polynomial time, essentially, right? Like the problem underlying the splitting of large primes as they get larger. Finding the prime factors of larger and larger integers is in this class. So yes, there was a perceived computational bottleneck in the classical space, and that's what was busted open with the advent of quantum algorithms. So Peter Shor's algorithm from the early 90s precisely showed how taking, in fact, a very small advantage. It wasn't a very sophisticated quantum algorithm compared to the state of the art today, but it was the first one that demonstrated how, by taking small advantage of a strictly quantum phenomenon, would be able to entirely short-circuit this and make it accessible to very easily provably polynomial time quantum algorithms.
So something that was thought to be one way, 5 minutes, the other way, 800 million years.
Absolutely.
Is maybe there's a side entrance of approach via the taking advantage of the quantum information phenomenon.
Exactly. And it wasn't, okay, so one might misconstrue this, as we're talking about now, as having to do with the material nature of quantum objects, like, for example, the actual instantiation of qubits. It is related to it, and certainly it was inspired from that, but the actual insight, the way that its discovery has changed mathematics and physics, is in realizing it as a new concept. In other words, what a quantum algorithm is a new class of computable objects, a new notion of computation. And for a while, people have been saying, including the founder of the field, David Deutsch, for example, and Peter Shor himself, who discovered this algorithm, would say that even if we never develop general purpose quantum computing, if for some reason it happens to be beyond our technological means, they didn't know that at the time. We're much closer now, but we're still not there yet, and it still might prove practically impossible to fully achieve its full potential. We don't know that. Nevertheless, the discovery of those algorithms and the development of these diagrammatic tools, for example, for rethinking, reconstruing what an algorithm is in these terms, revolutionized the way we think of what we now call resource theories, for example. In other words, thinking of what is possible in a physical system by looking at what is allowed to be done with the information that it contains. How does it operate how does it manipulate the flow of information?
And once the logic is out, once the way it works out, the material, hardware, infrastructure, or whatever you want to use to build that, it doesn't really matter anymore. I mean, you can probably get there through anything.
Well, in fact,
I
think you're more right than you realize, perhaps. which maybe speaks to the fact that you're an artist and your job is to be seeing things before you realize you see them. In fact, I think the realization over the last 20, 25 years that this is possible to do, that this is a class of things that can be done, that, that we can rethink of computation as being this other realm, right, this richer realm, has opened our eyes to recognize possible substrates for where that will be that we wouldn't have thought before, right? So this, within physics, within the space of sort of many body systems in theoretical physics, we've been recognizing this novel state of matter called highly entangled matter, right? Which is basically the state of matter that we want to have in a quantum computer. That doesn't necessarily mean it has to be made of photons or electrons. It could be made of things we haven't even thought about yet. It doesn't have to be elementary particles. It could be ions. It could be vortices of some sort of fluid or something. But essentially, we were abstracted away from trying to explain how a photon behaves to describing how the information that is carried by the photon behaves. And then that process, that way that the information is processed, can be transplanted to work in a fluid dynamics problem, for example. That has nothing to do with photons.
Or anything becomes the logic behind everything.
Yes, that's right.
The idea of a transistor and then making a functioning transistor, those are two separate things.
Exactly. Yeah. And now we have photonic transistors, for example, that they never thought about back in the 50s. Here's an idea for you. Part of the power, the magic of quantum information lies precisely on transitioning from, this is the way I describe it in my class, transitioning from the world being populated by answers to the world being populated by Q&As. And this is important because Q&As can be strung together. You can ask a series of questions before expecting the answer. And then each question creates a context for the next question. And what happens in quantum systems is that the answer you get will depend on the sequence, the order in which you ask the questions, because the context will change over time. If instead you thought the world was populated by just answers, well, those answers just are, irrespective of whether you ask the questions or not. So it wouldn't even have occurred to you. You wouldn't have been creative enough to open that space of how else might it be.
And those answers is in the scientific fields that also hold on new discoveries eventually in the math world too. And I wonder, Kilton, what is your opinion about this? Because you are not, I mean, you are mathematicians, but you're not coming from the college, the academic world. So what is your opinion about?
You could say a late in life mathematician.
Maybe late in life mathematician.
An amateur in the best possible meaning of that way, in the original meaning
of the word. Of the thing.
Exactly.
That's right, as opposed to someone who perhaps
professional
does that for money. Exactly, right. The question and the answer, the question asker and the answer provider are co-creating a world. You get the universe based on the questions you ask.
I love that. And this is related to earlier, you mentioned my work in my very preliminary work, I should qualify this, around quantum consciousness. And one aspect of this has to do with what you just said, Kilton, which is a sort of, I take a rather epistemic perspective, which is to say that what I almost consciously eschew the question of ontology, of what the world actually is in its true nature, not because I don't find it interesting, but because I don't find it accessible. Because I think that what is more interesting for me at this point, and possibly closer to making progress in, is how the world, how our model of the world, what we interact with, which is always going to be a model of the world, is informed by the questions we ask, by the framework, by the stories we tell. The stories being stringing together as a composition of questions. Some of them contingent on the answers we get, some of them are contingent on the questions someone else will ask. So it's sort of intrinsically collective endeavor to do. And we build this notion. For example, just to be concrete, one idea is that the world is populated by elementary particles. There is a handful of elementary particles in the standard model right now, and we think that the world is populated by those particles, material world, right? It's a model of the world.
So Kilton was working on this algorithm system for computer vision and to make it more efficient as much as possible. Pretty much, now you explain it better than me, but pretty much to make this of almost intuitive kind of computation in the way the machine can see, understand something immediate, right? Immediately.
Yep.
And because of that, he found some connection with the quantum theory, or at least then when you started to be interested in quantum theory. Is that correct?
Exactly, yeah. To have computer vision, real-time AI, so things that will eventually be robotic, and interfacing with the real world, to have them understand the real world and how it moves, similar to the way that we do, the ability to catch a ball, not by doing computation, but just having an intuitive sense of where it will be because of the way that it moves. This is all stuff that seemed to need a new bit of math that I called at the time a reality convergence module. What I think is going to be where the ball will be and where it ends up, and then adjust from there and learn I need to move my hand a little sooner.
Right.
And because
it's the right language.
Heavier.
And just, it's the right language, which is sort of like the appropriate abstraction layer, possibly supported by lower layers of abstraction, but creating some sort of grammar, if you will, that supports that language at that level. Let me ask, although I think I can guess the answer, but I will ask, how do you feel about the idea of seeing not individual pixels, but seeing the world as populated by objects? Right? So, for example, I'm not decomposing you. I'm not decomposing you into the pixels and then at some later stage say all these pixels fit together. And I'm expecting to see people. Right? There's probably a lot of noise in my visual field. I don't even notice them. I don't even observe them.
That's right.
Because our brain is sort of supremely tuned to finding patterns. And the noise won't have patterns. So generally speaking, we avoid that. We just aren't even aware that there is all this noise, right? So we zoom into the patterns. The patterns are people, faces, eyes, various things like that. That's what we're going to see. And there's evidence for this in all the misapprehensions we have, where we see eyes appear in bushes, let's say, or in the sky or whatever. I mean, that's just, so our processing is very different from the sort of very bottom-up, if you will, approach that computers do, where we just have to, we think of the world as being entirely pixelated and then have to build from scratch everything.
Exactly, that's right. If we assume that we ourselves have some kind of a data feed that we never see in raw form, then we must be something equivalent. And the perception arises from what objects you are trying to make from that noise, which could be thought of as almost pure. There's infinite spectrum.
It's a resource, and the question is what is allowed, at least in modern the parlance, if you will, within resource theories, is what are the set of possible things and what are the set of impossible things? Generally speaking, in fact, you delineate the space of impossible things, the things you can't break, the symmetries you have to obey, and then everything else that remains is possible, and then your job as the creative is to explore that. How different could the possible things be from one another? And if they're possible, that means they're transformable into one another. So from one, you can go to the other. So this is a non-constructive way of demonstrating the existence of an algorithm, right? If they're both possible, there must be an algorithm that transforms one to the other, even though we haven't come up with it yet. And that would solve, for example, a cryptography problem, right?
Going back to the quantum consciousness, though, can you explain a little bit the theory that is also biological?
So there are several connections, and I also do teach a class that I enjoy very much. In fact, it's culminating, I've taught it many times, and it's culminating these days on computational biology, and a big theme in that is neuroscience. And within neuroscience, the big culmination is around how consciousness arises out of neural networks, out of the connectome, different theories for that. And so it is inspired from that, and as well because my brother is a neurosurgeon, so I had exposure through him and various other friends of mine. I have a lot of doctors in the family. Yeah. So, but I was fascinated by the complexity of, let's say, the brain in this case, various biological problems, and how the approaches that we apply to physics, this is now work that I was doing in the 90s and the early 2000s, the approaches that we apply from physics don't seem to apply because in physics, what works well, at least in the physics of the universe as we populate it now, things tend to be small approximations away from equilibrium, right? We generally compute equilibrium and then just tweak them a little bit and say, okay, how will they revert back to equilibrium? Well, that doesn't work for life's processes because the existence of life is in some ways a far from equilibrium thing. The only equilibrium is death.
It's never in balance.
Right, it's never in balance.
But every moment it is.
It feels like there's a notion of homeostasis, right? Which is a dynamic equilibrium. So it's a very different notion of equilibrium. We need different, so the traditional perturbation methods wouldn't apply. So I was fascinated by this early on in my career. I got my PhD in '95. So over the first 10 years, I worked a lot with biologists. Including my wife, who's a medical doctor as well, and we did work in theoretical immunology. So in various fields in biology, the question was, how does complexity arise in life? And how is it held together? It's seemingly against the second law of thermodynamics, for example. My intuition was that, and it was an artistic intuition. For me, math is like my art, my language. Was that we just were using the wrong mathematics. I strove to describe that a little bit. The mathematics that we doubled down on was the one that worked decades earlier in physics as these sort of perturbation methods, but those were unlikely to work. We needed new mathematics, and so that started my path that I eventually culminated in this applied category theory perspective. And so within the space of consciousness, now I should say even before my direct personal involvement, there have been other people speculating around possible quantum effects that underlie in an irreducible way consciousness. Most famously, Roger Penrose, the physicist, wrote a couple of books in the early 90s around that. And it was rather controversial. At the time, it was very speculative. There was very little evidence. In general, for any quantum effects in biology, let alone specifically in neuroscience and in consciousness. Interestingly, his main argument was around what he perceived to be the non-computable nature of mathematics. In other words, he was using the fact that humans can do mathematics as a tool to probe the nature of consciousness and say that because the nature of mathematics, in the way that we resolved what is traditionally called the crisis of foundations in mathematics in the beginning of the 20th century, with Gödel's incompleteness theorem and so on, the way that this is traditionally resolved in the minds of working mathematicians is that mathematics is a more open field. It's not constructible in a traditional sense that earlier generations of mathematicians thought would be. The notion of truth is not entailed in the finite. We can go on and talk a lot about this. This is a philosophical topic, but in any case, Penrose, in a what I consider to be a tour de force, basically a philosophical tour de force, used this as an insight to demonstrate with concrete examples as well how our ability to come up with these brilliant insights about abstract objects demonstrates something beyond computation, that mathematics is beyond computation. And in his mind, he thought, and the quantum computing paradigm had not really become well known at the time. I mean, David Deutsch, who started it, did so in '84, '85, but by the late '80s, early '90s, when Penrose was writing that, he was very vaguely aware of it, and it had not caught on the way that it has. It started in the early 2000s, basically, to really catch broadly. So these are just formative ideas for me. So over the years, I worked on two separate models of the neural connectome. in terms of, because my field is, as I said, probability theory, stochastic processes, and especially work on distributed stochastic systems. In other words, randomness, different random elements that are spatially distributed and they interact with one another and constrain one another, like economies, for example, or
chaos
networks.
at large.
Well, yes. What does it mean? One of the notions there, by the way, is the seeming mysterious. Some seemingly mysterious force that guides these systems in many instances towards what Stuart Kaufman called the edge of chaos, right? So yes, chaos, but chaos as a resource, not chaos as something you get lost in, but chaos that you're just at the edge of, that you take advantage of as an engine for newness, that life, presumably, and maybe very specific life processes like the brain might take advantage of. Anyway, these were, again, as I said, formative ideas. But I had worked over 20 years on a couple of separate models of the connectome as data on the human connectome and other connectomes of other animals started coming online. Data became possible through fMRI studies and other studies. It was a natural test bed for mathematical ideas, especially ideas having to do with randomness. One interesting idea, by the way, that for me, it's become, for me, an organizing principle, is that randomness is also a resource for the brain. So in fact, when the brain acts, and this is now being quantified in particular ways, when the brain activity is very synchronized and there's very little randomness, it is basically unconscious. So consciousness is highly correlated with some amount of noise being there. Not entirely everything goes noise, but some amount of noise needs to be there to enable it to be poised, so it can be responsive. It can change states easily. So that's an interesting sidetrack. That paper came up with basically a series of 4 or 5 attributes that would be kind of epistemically correlated with a conscious state, including this, one of my favorite ones, probably the first one that I came up with, was this notion of non-ergodicity, which is a probabilistic notion. So, well, it's a notion from dynamical systems, but has a particular valence for probability theory and stochastic processes, which essentially is an example of something we were talking about earlier, where you were saying, Paolo, and I think very insightfully, that the value of mathematics is in opening, or this is how I heard what you said, which is that the value of mathematics isn't even in the concrete applications that it has, but that in opening new ways of seeing the world, new ways of realizing things that are possible.
So to condense, our brain is doing quantum math, or what do you think?
So yes and no, and I don't mean to be facetious about it. And what I mean is the only thing I can say is that it is doing something that is analogous to the math we use to describe quantum processes. Whether it actually physically takes advantage of quantum substrates to do that, or has found some other way to do that, so the physical aspect of how it does it, or it's pre-endowed with some other resource that, I mean, there's a whole host of theories of consciousness, and my work on this, preliminary as it is, and fascinating. I want to do more work on this, obviously, still. And in fact, as I was saying, earlier, yesterday even, I had one of my collaborators come to visit my class, my computational biology class, and talk to us about actual experimental evidence of these types. And so I'm working in this field, but I would not claim that my work is shedding light on the probability of there being quantum substrates in the brain, only because that I think will require actual experiments, on nervous tissue. I'm more interested in properties of the systems, right? So to rephrase my answer again, I do believe that in order to attain the conscious state, my best understanding at the moment is one of the necessary ingredients is an aspect of the math that we use to describe quantum systems that we've learned about by our studying of quantum systems.
Right, and also because then we can say that quantum math is everywhere after all, right?
Exactly. I like how you put that. Yes.
How can that not be? Are we?
Because we're
something
bringing
different?
it, and because if our consciousness, and therefore the ways in which we perceive the world, the stories we tell of the world, right, and the questions we ask of the world, are driven by this quantum, and I'm liking that you described it as quantum math rather than quantum physics, right? Like it's the math, that we, right? Therefore, it's everywhere because it's going to be imprinted in the answers we get and in the stories we tell about the world.
Everything we can see, everything we can measure would already have the results of it in it. So as we deduce it backward, it's the tool we use to think about it. The only question left is, what's the user of that tool? But it's clear that it's a tool, and that's Penrose, right? It's a tool, and therefore there's a user. And that might not be answerable from here.
So whether we are, so this is, I think the question that, Kilton, you're raising is it, well, one way I'm seeing it is it an open system or is it a closed system? And, but I would also add that even if it were an open system, another possibility to the one that you described, that there is somebody on the outside, is that we're all also on the outside, that perhaps we're all in some sense infinite, or we have access to some sort of infinite resource. We just don't perceive it in any instance of the universe at the same time. And so that might be okay, this is very speculative. What I just said is obviously very speculative, but to bring it to something more concrete and that is close to questions that people are asking in physical systems today, what might be the fundamental source of new information that seems to be what comes up in quantum systems?
Right.
Now, you could either argue that real existence is over essentially an infinite set of counterfactuals, so that we're really just one instance of, we're only experiencing one universe, but in reality we exist in all of them.
It's a deeper
or in some sense,
thought.
Even if there aren't multiple parallel universes, even if their universe is only one, in reality we still have access to some sort of infinite potentiality, and that's what makes information in the universe not be conserved, essentially. We can actually have, because, previously I mentioned the non-ergodicity, I mentioned path dependence, but a natural question that a physicist or a reductionist would ask is, well, where is that coming from? So and it's a valid question, right? In other words, if you've specified all the initial conditions at the level of specificity that you need, and you move the thing, how is it that it could be, in the end up in two different places? What could have given that choice, right? And so what I'm saying is that, perhaps a mathematical way of describing it is that the object, you're only incompletely specifying the object. And the object itself has access to infinities that are beyond what we're describing right now. And so at those points where it is choosing, let's say, it is accessing these previously inaccessible aspects of its essence. So something of that kind needs to be there, I think.
Closed system, open system, probably both. Closed while we use it, open as soon as we let it go. And what's the next? Whatever we made from the undescribable, right?
I love that idea. The more we use it, so when we are trying to exploit it, it becomes closed. We have an actual set.
More and more closed, actually.
Right? Indeed. And so, whereas in the space of creativity, because I work very much in the area of creativity in math, how can we elicit creativity in the math classroom, how we can demonstrate to the population at large that math is a creative and there is a language, and therefore there are stories to be told.
It's okay to play with it.
And you have to let go a little bit. And I think, this seems very abstract and not well specified, but I'll tell you this. The way that I see it, at least within the context of category theory, this applied category theory paradigm, is that it is a language that allows you to rigorously propagate ambiguity. In other words, if you attempt to disambiguate, if you ask at some point in the middle, well, what is it exactly that you're talking about? You're missing the point. That's not to say that you're saying anything goes. But the objects that you're manipulating, you're endowing them this ability to mean multiple things, some specific multiple things, and your grammar, so the language structure, allows you to propagate them in consistent ways that formally make sense. And so you don't have to disambiguate. This is very much like quantum computation, right? Like that's
bounded uncertainty is not complete chaos. It's a composable Boom. Fantastic phrasing. Say that again. You said a rigorous?
So I think it's a rigorous propagation of ambiguity.
Wonderful.
Yeah.
I love it.
I do think category theory offers tools to do that, and I think it's untapped resource in communicating mathematics, for ourselves, even mathematicians themselves, to see their practice through this lens.
So cool.
So, yeah.
Nice. Cool.
Well, I'm glad we had this conversation.
Yes.
It ended up being, very
That's so great. Let's talk more. Yeah.
Absolutely. Yes.
Thank you so much.